So let's begin by learning how we can graph a polar equation. And one way we can do that is by point plotting. Similarly to what we've done in rectangular coordinates, we would develop an XY table and find coordinate points. Because remember, every XY that we were able to find, if it satisfies the equation, it was a point on the graph. Likewise, when we have a polar equation, we're looking for all the points, all the coordinate points in polar form, r and theta, that match and meet this equation. So let's go ahead and draw what we call our theta table. So I'm going to choose some variables of theta. And the variables of theta that we would like to choose, so let's choose some angles that we're already familiar with. We already know what the cosine of those angles are. So for example, 0, pi 6, pi thirds, pi halves, pi 6 pi, and pi. So there's about 7 points. That's enough to kind of get us a start to see what this graph might look like. So what do we do now? Well, let's take this value of theta and plug that in. So this becomes 4 cosine, let me get another color for you. Cosine 0, which equals 4 cosine 0 is 1. And so then I have some r equals 4. So we were able to find one coordinate point. So just sit back, have some popcorn. I'm going to go through and plug in the rest of these for us. After plugging all those in, thank you for sitting back and watching. We found out that for 0, 4 matches up, pi 6 and theta matches up to root 3. And all these points that I have here now represent solutions to this polar equation. So let's stop for a second, find and build our board, and then we can start plotting some points. Now we're going to be using a lot of polar coordinate types of grids. Now remember, a polar coordinate grid looks like our traditional XY axis. However, our x-axis is really the polar axis, and then we have the line theta equals pi halves, which is the vertical axis, and then concentric circles every so mark, whatever your scale is, out from that. Because remember, a point in polar coordinate, or a coordinate in polar form, is both a radius or a distance from the center and an angle. So let's go ahead and plot some of these points we have. The first one, we have an angle of 0 and a distance of 4. The second one I have is an angle of pi 6 and a distance of 2.2 root 3, which my calculator says is roughly 3.5. So on the angle pi 6, out 3.5, 1, 2, 3, right about there. The next one is at the angle of pi thirds. Again, we chose those angles because we know their exact values. Pi thirds is at a 2. Pi halves, at an angle of pi halves, we have a distance of 0. In the 2/3 direction of an angle of 2/3 pi, out that direction, we have a -2. So remember, our angle is in the second quadrant, but since we have a -2, it goes backwards, so it reverses itself into the fourth quadrant. And that was a -2. My scale is a little off, folks, so apologize for that. In the 5/6 direction with an angle of 5/6 pi, and we have a -3.5. And then pi, in the angle of a pi, and it has a -4. That puts us right back to where we started at. And then the cycle continues from there. Our goal next is to look at those points. Notice that pretty much the reason why we use polar coordinates is because a lot of our functions are circular in nature. So I'm going to connect these points in a nice circular fashion. And there's the graph of r equals 4 cosine theta. Now, do you remember that we were also able to convert from polar equations to rectangular equations? So let's see if we can remember. So if r equals 4 cosine theta, r also equaled, well, let's multiply both sides by an r. R squared was an x squared plus a y squared, if you remember one of those identities that we had. R cosine theta was an x. So from there, we were able to go ahead and convert from polar coordinates or a polar equation to a rectangular equation, which means that we have variables in terms of x's and y's rather than in terms of r and theta. Let's work this down a little bit further. Let's subtract 4x from both sides. We're going to complete the square over here. The reason why I want to complete the square, because then I can complete a perfect square right here, which is an x minus a 2 squared, plus y squared is still a y minus a 0, and then 4 is a 2 squared. The reason why I did that is, do you remember or recognize the standard form of a circle, which was an x minus an h squared plus a y minus a k squared equals its radius squared? So if you're able to see that, then you're able to see that this equation represents this circle that we were able to draw, where I have a center point at the point 2 and 0, and then every point from that is at a radius of 2 units distance away. So we can graph both in polar coordinate and rectangular coordinate. We can convert from rectangular or from polar coordinate to rectangular coordinate, or rectangular coordinate back to polar coordinate. But I just wanted to show you that because the graphs both line up. We're going to start to notice some patterns popping up over throughout this series right here. So I want to draw your attention to a couple of the first patterns revolving circles in polar coordinates. Where I have a circle that kind of roughly sits on the polar axis, that usually follows the equation of r equals a sine of theta. And a represents the diameter of the circle. And that's true for all a's greater than 0. Now, if I take that circle and kind of flip it over so it butts up against the vertical axis, or the line theta equals pi halves axis, then I have r equals a cosine theta, where again a represents the diameter of that particular circle that we graphed. So we will see circles in polar coordinates, and we'll typically see patterns that follow along those lines. We're going to introduce to you a lot more, but we just want to kind of start to get a feel of what we're beginning to learn, explore, and see.